Stream. Let's see if
It
that's
says
true.
meeting is now streaming live.
Yes, it does.
I'm not sure if we're on or not.
We are on.
We are on.
We are on. Okay. I'm going to take that as a yes, we are on.
Okie doke. Well, welcome everybody. I'm Dr. Daniel Barth here with our ninth exciting episode of the How Do You Know show.
That's right. And this is now the countdown. So
This is now the countdown. Okay, so we'll be actually on show in 5 minutes.
Yep.
Okay, that works.
Does that work for you?
Works for me.
Okay.
Works for me. Those of you who are tuned in already, we'll get started in just a moment. Scott and I have been having a fun conversation about telescopes, binoculars, asteroids,
Yes. Impacts, craters.
Yes. Everyone has a few
They
asteroids
go boom in the
their
night.
life. Don't we all have an asteroid or two in our life? I'm sure we do.
Oh, yeah. Sure we do.
Let's see.
Let's see. So who logged in first? We got, I think it was Mike Wiesner. No, it was Book Davies. Yep.
Hey, there you
Mike
go.
Wiesner was right on his heels.
Mike, glad you're here.
He says, yippee, he can speak. Cameron Gillis is in the audience right now. He's going to be coming on here in a few minutes.
Okay.
Yeah, right after you, Daniel. And then Book Davies is on, and we've got,
Always enjoy Book Davies' comments.
yes, Richard
And I do read
Race.
them, folks, by the way. I do read all your comments after the show. I don't see them live. I've found out how to do that, but I find it a little distracting. And if there's really cool questions you'd like to ask, put them in the comments and Scott can forward them to me. But as you know, this is live programming and keeping everything straight, being coherent, and reading questions to answer on here.
Oh, yeah, doing gum and walking and
Yeah, kind of. Not a
and
professional
writing at the same
broadcaster,
time with
just
both hands. Yes.
an old-time astronomer and science teacher.
We have a viewer from Pakistan. So
Outstanding. Welcome.
yeah, yeah.
Glad to have you
Karachi,
here.
Pakistan. Abdul Sadr is watching.
Abdul, nice to
We
see
got
you.
Pekka from Sweden.
We always have our Swedish contingent.
Yes, that's right. Mike Wiesner. Did Scott drop his mic? No.
No, I'm hearing Scott just fine.
Yeah. Abdul says it's late night here in the East.
Yes, they're 12 or 13 hours ahead of us, I think.
Right?
Something like that. So yes, it would be, oh goodness, he's up in the wee hours of the morning.
Yeah.
Well, so glad you've made the effort to join us live, Abdul. That's really exciting.
Cool. We have Harold Locke says, Wild Wednesday here. Good afternoon, early evening to all. Norm Hughes says, hello, everybody.
Hey,
Martin
Norm.
Eastburn says he's here as well as reading Skies Up magazine. So that's cool.
That's outstanding.
Yeah, you have you've contributed to Skies Up before, Daniel.
I have. I contribute regularly to Skies Up.
Yeah. Um, and a little congratulations to engage the audience, please. Congratulations, Abdul. And thank you for being part of our program. Chris Larson says hello, and Norm says book, and Norm says Chris. It's funny, the interaction that we have with the audience. It's cool.
I noticed that every once in a while they're like, "Good
Oh.
job, Doc," and I love that.
Harold Locke says Skies Up is a great publication. Thank you very much.
It is indeed. It is indeed. Very proud to contribute to that in my small way.
Well, it's no small way. You do a great job.
Yeah, in a way, the STEM Corner articles are kind of a precursor to this program.
Yeah, I can see that. Here we go. You know, Daniel, this video of the LRO barnstorming Giordano Bruno crater.
Yes.
I thought maybe you could tell us a little bit about
Well,
it.
this is just beautiful. And one of the first things you notice, Scott, is when it pans up and you look up the sides, you can see clear evidence of sliding. And you see some massive material that slid down from the edge. Craters, when they initially form, tend to be very deep and cone-shaped and pointy, but they're gravitationally unstable. And you can see the pile of rubble at the bottom where the crater walls have broken away and slid. You can see boulders that have traced lines down there. You can also see evidence that this crater rim has been forced out and upward. And that's some of the things that we're going to be looking for today. We're not going to see this kind of lovely fine structure in our large scale model, but and this picture makes it a little hard to see the structure of the rim. And you've been, of course, to Meteor Crater, otherwise known as Barringer Crater out in Winslow, Arizona, Scott. And I have too. We'll talk about that today. One of the lovely things about Barringer Crater, and I noticed this when I was driving there, it's out in the middle of nowhere, literally. And there's a road that leads basically there and nowhere else. And as you're driving up, you see what looks like a hill. And it looks like this mesa, this plateau.
Right.
And as you get up closer and you drive into the parking lot and you drive up towards the visitor center and you're realizing, oh my God, it's not a hill, it's a rim.
Right.
But it's just this, it's perhaps 50,000 years old. And you see this beautiful structure. And when I walked down, they wouldn't let me walk down in. I asked, but they said, no, I'm sure you have to have a lot of pull and arrange many months in advance. Yes. But I asked anyway. I flashed my ID. I'm Dr. Barth. And they said, they were the person at the visitor center was not impressed.
I tried to pull something like that too, but I didn't have the doctor part, so.
Yeah, it didn't work for me. So anyway, but I walked down onto the platform. They've got a platform there built out, hanging over the rim. And you can look out to the right and you can see layers of granite that have just been folded back. And you're realizing, oh, I'm looking at a layer of granite where the rock is actually folded. And I was able to find a lovely photo of this. And I'm going to go ahead and pull this up. This is not, I looked really hard for my photo of Barringer Crater. I could not find it. But I went ahead and I found a photo, and I'm going to go ahead and share this with our viewers.
Cool.
And this is very much like what I saw
Wow.
in Barringer Crater.
What?
Yes, yes. There's this area where you're looking at layers of granite, basically.
I look at it, it's just like bent. I mean,
It's folded like a layer of clay.
yeah.
And I pointed this out. My son was with me. I said, look, the rocks are folded. And he says, no, they're not. I said, yeah, here, take the binoculars and look. He goes, how did it form like that? I'm like, oh no, this is layers of sandstone and other things out in the desert. But the amount of energy yielded by an impactor, the Barringer impactor, they estimate about 80 feet, which translates to roughly 50 meters. So you're talking a 50-meter object, and it's coming in as something outrageous like 30,000 kilometers per hour.
Right.
And they think it was almost straight down. So to the natives who were there at the time, and there would have been people living there at the time, and if you were far enough away, you would have been able to survive the event. But it would have been like this spear of light. And it would have not been instantaneous, as we know from the the Chelyabinsk meteor. They would have had time to see this spear of light coming straight down and striking the Earth. And then, depending on how far away you are, a matter of seconds, you start to feel this great shock waves. If you were close enough, if you were just on the edge of survivability, you might have experienced something like a magnitude 7 or 8 earthquake. And then a short time later, the sound would arrive, because the earthquake waves are actually supersonic. The sound arrives, the great thunder, and the wind follows. You're getting 80, 100, 120, 150 mile an hour winds, depending on how close you are. And then it's several minutes later, the rocks begin to fall from the sky.
Mm-hmm.
And to survive something like this, you would have had to be 25 or 30 kilometers away. Everything in basically a 100 square kilometer area. So you figure everything within 10 or 12 kilometers, absolutely obliterated.
Like vaporized.
Yeah, and you're talking about even if the heat pulse at 10 kilometers away will set your clothing on fire. Ooh. Grass and shrubs and trees are being ignited from the heat pulse. And then the earthquake comes, and then the winds, the supersonic winds arrive, and then rocks, the size of your
that wasn't
fist.
Enough. Rocks.
Right. Rocks the size of your fist start raining down, and enough rock to make a layer at 10 kilometers out, half a meter deep. And so you're realizing, you're not in the survivable zone.
Yeah, it's a bad day.
It's a bad day. It's one of my favorite phrases. It's a bad day. So yes, it would have been a stunning event, and the pressure and heat at impact was sufficient to take these layers of stone, heat them enough, and put them under many kilotons of pressure. I suspect as much of a megaton of pressure. The heat, and under that much heat and that much pressure, the rock becomes essentially pliable. For a large impactor striking the surface, there's no realistic difference between solid and liquid. Everything liquefies and becomes pliable at those pressures and temperatures. And the rock is peeled back, and material is shoved out, and you're taking all this downward vertical force, and the impact, the earth is solid, so the impact is spread out and turned horizontal. And so Barringer Crater has a volume equal to roughly 400 professional football stadiums. It's an obnoxious 400 professional. You've been to Razorback Stadium. I'm sure a lot of our friends have been to either American or European football stadiums. We play different games, but it's the same kind of facility. You realize, okay, 400 where Manchester United plays. You have 400 of those, the 400 Rose Bowls. And it excavated this in 5 seconds.
Oh,
just outrageous amount of energy.
Right.
It really makes our tiny little nuclear firecrackers pale into insignificance. The Chelyabinsk, the Russian meteor, is what it's colloquially known as, exploded over the town of Chelyabinsk in Siberia. 400 kiloton explosion when it hit the atmosphere. Now, those 400 kilotons are spread out over a period of time, for one thing. It's not an instantaneous explosion. But you start to realize, oh, Hiroshima is 15 kilotons. Nagasaki is roughly 20. And so you're talking about an impactor that's delivering, what, 30 times the energy of the Hiroshima bomb?
So they must, I mean, if there was anyone around to hear it 50,000 years ago, and there most certainly would have been.
There would have been.
Yeah, somebody must have heard it. What must have sounded like a tremendous thunder, you know?
There are people who witnessed the Tunguska impact.
Right.
Now, nobody talked to them for almost 30 years. I think it was 27 years later that people from the University of Moscow went out. It happened in 1908.
Yeah, and why was that? Because of secrecy or something? Or?
It's very remote.
Yeah.
Very remote, and they started to get these reports. No one from the modern civilization in Moscow. I mean, the people who are living out there are living, I'm sure, much as their ancestors had done for many, many, many thousands of years. They're very primitive people living in a very primitive and remote environment. Mm-hmm. And it was after World War II when these reports started to filter in. The World War had made people more aware of their boundaries and their frontiers. And they started getting reports, and people who were going there to explore for oil and whatnot. And they're coming back and they go, you know, there's this area where there's almost 800 square kilometers. And all the trees are knocked down in this lovely radial pattern, and they're burnt on the top and they're frozen into the permafrost on the bottom. And what the heck? And everybody's like, you were too much vodka, comrade. But no, they sent people out there to investigate, and they found out that indeed there had been this terrific impact. And we know from climatological records that the Tunguska impact lowered global temperatures for upwards of 5, depends on where you were. Northern hemisphere, about 6 or 7 years. Southern hemisphere, about 3. Mm-hmm. And it made this tremendous global impact. And there's argument about what it was. And people have said, oh, there's no stony fragments, so it must have been a comet. Maybe. Something hitting the permafrost would have certainly, something coming down almost certainly vaporizes before impact. And vaporizing before impact and then hitting permafrost, it's going to be like a power drill through butter. It's just going to go way deep into the interior. So whether it was a comet or a meteor, asteroid fragment, nobody knows. But it would have been comparable to the Chelyabinsk meteor, except the Chelyabinsk meteor, almost all of the detonations, it was a grazing meteorite. And so almost all of this was happening 7 or 8 miles up. It's still knocking down walls and blowing out windows. Friends, if you haven't seen, go to YouTube and type in Russian meteor. You'll find it. It's actually called Chelyabinsk. Don't ask me to spell that. I could give you an English spelling, but it wouldn't be Russian.
Sounds like it starts with the letter C somehow.
Yeah. So put in Russian meteor and you'll see these lovely videos. And there's some amazing videos security camera videos of people, and some people are holding their handy cams. They're holding their cell phones and they're standing there, and then the shockwave literally knocks them flying. And you're realizing, oh, this shockwave is hitting from detonations that are occurring 10 or 12 miles high. And the shockwave is penetrating down and it's knocking down walls and blowing out windows. Just astounding.
Yeah.
So you think of these tremendous impacts, and the moon is lovely. The record of violence, people say, ooh, craters. It's kind of like saying, ooh, nuclear explosions. It's astonishing. And because I have friends in low places, Scott, I have many hours of film of nuclear tests, both American and Russian.
Oh, wow.
And there's something called the Sedan crater test. They had this lovely idea: let's use nukes to carve away passes through the mountains so we can put in highways.
Oh my God.
And they took the Sedan test, I think was it was about 100 kiloton device, and they buried it about 400 feet deep, and then they set it off. And what you see in the time lapse is the ground rises into the 400 feet high, and then the flame starts erupting. And you're seeing, what's really cool is after the explosion, you're seeing house size, car size, chunks of rock, and they're trailing streamers of dust through the atmosphere as they fall. And you realize this is, then they back off the zoom. This is a way telephoto shot, I'm sure. And you look at the crater afterwards, and it very much is like a crater we would have if we had a sizable meteor fragment. The crater is about half a kilometer wide, about 120 meters deep. And they actually built a little rail system, and they had they were lowering people on a cable car to go in and take samples. And they realized, of course, using nuclear craters to do earth moving is a really bad idea because radiation and fallout and stuff. It's amazing some of the things they did, but you can find video of that, I'm sure. Right. But today we're going to talk about how do we do a lovely crater experiment indoors safely. And you can do it yourself. You can do it with students. You can do it in an outreach event. And there are a number of ways to do this. One of my favorite ways we were talking about before the show, I've done experiments where I've taken a box top from a Xerox paper box, right? A copy paper box, filled it with a mixture of plaster and sand, and then thrown rocks or used a slingshot, a catapult to fire rocks into it, and made lovely craters. And you get this massive, about 60 by 40 centimeter by 8 or 10 centimeter deep sculpture with craters and overlapping, and it's beautiful. We're not going to do that today. I have instructions for anyone who wants them, but it's a little more cumbersome. It's very messy. It's definitely an outdoor activity. And I'm going to push the boundaries of indoor activity today, Scott. Mm-hmm. We're going to make a little crater today. So I'm going to switch cameras here. And there we go. I have a can of blue spray paint. Okay. And I have what is here a cake tin. Surprise, I'm not baking anything in this one in the near future. This is one of the ones I just used. Yeah,
the paint icing might be a little.
Yeah, the paint icing would be a little bit. Edgy. This is a 9 by 2 cake pan, and for our friends overseas, this is about 24 by 4 centimeter round pan. And what I've done is I've filled it with about it's about a kilo of white flour, about 2 pounds of white baking flour. Now, I've spray painted the top of this. And I will tell you, friends, you cannot take and go, you're going to blow the flour all over the place. I took this into the garage and I put lots of newspaper on the floor and I put my pan down and I sprayed very high over it and let the paint settle down onto it. And why I'm doing that, the paint makes the surface of the flower adhere, which is comparable to a crusty regolith on the moon. And it makes a different color. So the material blasted out of our little crater will show off very nicely and it will look very realistic, I hope. Now, other people have done other things. I've seen toppings made with cocoa powder or with chocolate cake mix. And you put that in a wire sifter and you just sift it. If you have a flour sifter, if you're that old fashioned, if you're a baker, you put your cocoa powder or brownie mix and you sift over the top. I've also done this with cornmeal. And I've taken a sprayer with some clothing dye and I've sprayed the cornmeal to make it dark and then sprinkled over the top.
Why would you use cornmeal?
Cornmeal is heavy. Like it doesn't tend the thing I like about paint, it makes the surface material stick together. It makes an actual crust. Cornmeal, because it's heavy, makes an actual crust. The cocoa powder and cake mix has the same density as the flour, and it tends to get blown about more. There's less distinctness between the regolith, that is, if we're talking about the moon, the top layer of rock and rubble and dust, and the subsurface material that's down underneath. When we look at craters on the moon, Scott, we've noticed from last week's show that the surrounding area tends to be relatively dark, and new craters, the interior is very bright. It looks silvery white. The reason on the moon and on asteroids is that the surface radiation from the sun darkens that rock over time. It's called radiation darkening.
Okay.
And it comes from ultraviolet, gamma, cosmic ray, and all sorts of things change the chemical composition of the top millimeter or so of rock. But the rock underneath, after the impact, it's pulverized, it's powdered. And because it's ground up very, very fine, it reflects the light really, really well. And so during full moon, when we're looking at the sunshine coming directly down onto the surface, this ejected material called ejecta, surprise, is much brighter white. And I think we can see an example of that really quickly. Let me go ahead and take a look at, oh bother, here we are. Let's take a look at our full moon. Come on. Sorry. Oh, and now it's saying that I have to get a new flash drive because it's saying that nothing is there. Okay, here, let's take a look. I'm going to share this. There we are. So I'm sharing this beautiful image, and I'm going to go ahead and blow it up a little bit here. And this crater is Copernicus, and you can see this lighter material that's dusting all around it. Take a look at this crater right here, and I'm not sure what this one is, but you can see that the rim is bright and the area around it is lighter in color. And lots of these smaller craters that appear white in color, what you're seeing is something that's relatively new. There we go, we're sharing it now. Here's Copernicus. And here's some of these brighter white craters. And they're brighter compared to the darker surrounding surface. Can you see this ejecta pattern around this crater here? And Copernicus, of course, has a very large crater. This isn't a favorable view of the moon. Let's see if I can find a better photo very quickly. I'm not getting it. I'm not going to waste time searching. Anyway, you can take a look in your own telescope, and you can take a look at any video or photo of the moon, and you can see this. So we're going to try to recreate this today. So what I have today is I have a 25 millimeter marble, and I have a couple of smaller, I think they're 10 millimeter marbles. And so my desk is normally full of lots of things, but today, my friends, my desk is perfectly clean, and the vacuum is standing by because we're going to see some, I hope we're going to see some lovely stuff here today. So I'm going to go ahead and I'm going to stand up, and I'm dropping this from about 1/2 meter. There we go. And we got a lovely effect.
I heard the impact.
You heard the impact. Of course, on the moon, you would not. And I'm going to take my camera, and I'm going to put it right over the top here. And you can see the dark paint has done its job. And you can see that the ejecta material has covered the rim around the crater. We haven't actually got an elevated rim here. The impact wasn't energetic enough, and the flower isn't deep enough, but you get some lovely effects. Let's see if we can do a couple of other small ones, and we'll see what we get with some smaller ones. And I'm going to drop from a little higher here. There's an overlapping crater, and there's another one.
Now I know why you don't have anything else on your desk.
That's right. And so we're seeing, we've got some very lovely effects here. And you can see that the size of the crater, this one behaved a little oddly, but these two in particular, you can see that we've got a number of effects here. Let me see if I can grab something as a pointer. Sorry if this is a little wobbly. Here we go. Okay, so we have ejecta material. You can see some raised rim material here. And you can see for both of these that we have some streaks of material going out. And so this one, we have a very nice raised rim. And so we were a little bit higher when we dropped that one. And you can see that the some of the material that was blasted away, you can see some of the material here. This is coming out, some of this stuff coming out as far as here is blasting out about 15 centimeters from the impact site. Some of the stuff out here, there's a lovely pattern of ejecta and rays on the desk. So what we've got here is we've got some of these lovely, lovely patterns that we see on the moon. Now, what's nice is that with something like this, you can set this up, and it's very inexpensive. It can be done basically anywhere, and it can be done on a tabletop. It actually works really well to do it on a floor, where you have, you can use the vacuum, we would lay down wide strips of butcher paper, dark colored craft paper. You can get, schools have them. Mm-hmm. We would tape this down on the floor, and we would drop 200 and 300 gram masses from, and we would get a short ladder. And so we're dropping from about 2 meters high. And when you get that much of an impact, you get some lovely effects. The other thing I'm noticing as I sit here and watch, and let's see if I can show you this. I'm looking in here. Do you see where the wall has collapsed and some material has fallen down into the interior? Yeah. We saw this on the crater you had at the beginning of the show.
Yeah, that's right.
We saw this wall collapse. And this stuff is really gravitationally, this would go ahead and collapse, and just subsequent impact and other things. I suspect if I stood here and pounded on the table, I'm not going to do that, we would get a chorus of dog barking from downstairs. But you can see how we're getting now, let's see if I can get this focused. There we are. And we're getting a very nice collection of material. I'm going to take some photographs of this which I will post to Explore Scientific's page on Facebook so people can have a look at this.
Yeah.
But what we've got, Scott, is a lovely analog. I'm going to go ahead and switch back to my other camera.
Sure.
So what we've got is this lovely analog, and I'm hoping I can hold this up. We'll get a little better.
Oh, yeah.
I'm dribbling flour all over now. So I'm going to stop while I'm ahead. I could just see the whole thing landsliding into my lap. And that would amuse everyone who's watching the show, but not so much myself. So what we've got is a lovely analog here. And we can see crater rims. We can see ejecta. We can see ray structure. We can see elevated rim structure. Mm-hmm. We can see multiple layers of impacts. If you've got something with the cocoa powder on top, works quite well. And you drop one big object like and then proceed to smaller and smaller. In the end, you're dropping, birdshot or BBs. And you get this landscape of craters. And you can actually stand. I can't stand up on my desk and stand over it here. That's not practical. But you can stand over it on the floor. You can drop from a variety of heights. At least a 1 meter fall is best because you get this sudden impact. I find if you can find them, if you can take balls of clay and flatten them slightly, so you have this disc. The disc tends to catch the air under it and can make beautiful, beautiful ejecta patterns. I don't know. Should we try one gigantic disc impactor?
Try one. Yeah.
Try one. Okay. And so Scott's saying, yes, it's at your house, Dan, not mine.
Good. Yeah. I mean, you got the vacuum there and everything, right?
That's right. I got the vacuum and that it's science. So here we go. I'm dropping this as flat as I can.
Ooh.
So what do we have here? This is beautiful.
Wow.
So what do we have here? This, Scott, is a ray.
Yeah.
And why do we have it? Because the crater rim collapsed.
Right.
We're getting explosive compression of the material inside. The material inside the crater is being pulverized. Yeah, it's under many, many millions of tons of pressure. And if the ray collapses, we see that, the ejecta is channeled into this nice long streak. And what do we got here? I'm going to measure this because this crater measures about 6 centimeters. But what have we got here? 30. We've got material being blasted over 60 centimeters away. So we've got a ray system which extends more than 10 times the diameter of the crater. Right. And for crater Tycho on the moon, that's perfectly true. 90-kilometer wide crater. And we've got rays which extend over 1,000 kilometers. So this is not unrealistic. Why do we get that much ejecta here? Because it's relatively low speed and the atmospheric drag doesn't affect it much. Why do we get something that goes straight for up to 1,000 kilometers on the moon? It's because there's no atmosphere at all. Because obviously on Earth, if you had a Barringer size impact, all the gods forfend, please. Saints preserve us, as they say, my grandmother would have said. If we had a Barringer style impact today, the dust cloud would go up into the stratosphere and it would circle the Earth many times. We know that the Krakatoa explosion, Krakatoa 1830s sometime, 1835, something like that. And there were ships who were there and the dust cloud circled the Earth 7 times. So we know that these things get suspended in the atmosphere, whereas in the moon, they do not. And I'm seeing on my desktop here, there are lovely little streaks of material where clumps of material landed and skidded. The ray structures on the moon, as they get farther and farther out, perhaps a few centimeters thick, very, very thin. Perhaps even less than that, a dusting, literally a dusting of reflective material. They're not visible except during full moon. And at full moon, we see them because, like a reflector on the back of a car or a fence post, our light source is shining directly at them and directly back into our eye. And so this kind of a lovely, lovely demonstration where we have this beautiful ejecta pattern, and I'm going to take some nice pictures and post them for you. I'm hoping some of our friends will go ahead and do this. Very exciting. I've been asked by the National Association of Geoscience Teachers to do a paper and a presentation this summer. And that will be on the Clay Moon, episode 4 from How Do You Know? And so folks can go look that up. That's very exciting. I'm also doing a presentation this summer for the Arkansas Teachers of English to Students of Other Languages, the TESOL conference, because what we do here, Scott, when we make these models, these lovely models, whether they're Clay Moon or the impactors, every student who creates these things creates them in their own language in their head. Yes. And when we give vocabulary, that reflects experience. Then the words mean something. It's not, here, memorize this list. We're using words to explain other words. And if you don't speak a language well, that doesn't work very, very well. But language following experience works very powerfully. And I'm teaching, helping other teachers around the Midwest learn how to use STEM activities, what we're doing here on How Do You Know, to help students who don't speak English well learn how to master English, and to help native English speakers learn how to master scientific technical English, which is another skill besides regular fluency. Right. So those things are very exciting. We have links on the explorescientific.com/how do you know for the Astronomy for Educators book. It's really astronomy for everyone. We're in more than 4,800 schools in more than 50 countries now. I hope all of our listeners will download it. There's also a link. I'll make sure Scott posts it, friends. There's also a link for a survey. A short survey takes about 5 to 8 minutes. For my paper this summer, for my presentation about to the National Association of Geoscience Teachers, it would be really, really helpful if those of you in our audience who've been watching the programs, who've maybe downloaded and looked at the book, if you would take a look and take the survey really quickly. It's anonymous, and that would really help me in my presentation, because I can't tell you, I see so many teachers who are talking to me and posting on social media, oh my gosh, the year is over, because we structured these things where the tests happened in late April or early May, and then we have until June. And the teachers are saying, well, the kids know it's over. What do I do now? Are there good worksheets? Are there fun word searches? And I'm screaming, and I've pulled all my hair out. It's all gone. But I try to tell these teachers, no. Let's get the students engaged. Let's do hands-on stuff. Yes, you're going to learn. It's going to be applied to the standards. The kids are going to love it. And when kids are engaged, having fun, hands are busy, minds are busy. Surprise, Scott, behavior in the classroom is better. And this shouldn't be a mystery, but it needs to be taught. Yes. So I'm really hoping everyone listening today will, if you haven't got the book, get the book. So give me that link. Give me that link in this chat. I will. I'm going to. You guys want to be in the Cool Kids Club? Yes. Do you want to be in the Cool Kids? Yes, of course you do. You want to be in the Cool Kids Club, and I am going ahead and I'm going to get Scott that link right now. We have really cool people watching our program. We do. And if I was as clever as advertised, I would have this all ready to go. Of course I would. All right. So while you're looking for that, we're going to read some comments here. Please do. We have, let's see. Our gentleman in Pakistan was very interested in your program, and I have directed him to download your, your book and your teaching curriculum. And so Abdul says that he'll be reaching over. He says, we're on our way to visit a huge number of schools, colleges, and universities, part of our outreach program to promote space science education across a nation of over 200 million people.
which is awesome. I think people liked our audience liked your demonstration. It was fun.
Good. I'd also like to encourage Abdul to reach out to me and all of our viewers at astronomyforeducators@gmail.com. Abdul, especially for someone like you who's promoting astronomy education, happy to help you, happy to provide you with materials and activities and fun stuff like that. I'd love to reach out and help the teachers and children in your country learn more about astronomy and space science. And that, of course, goes for all of our listeners. Love to hear from you folks, and I will be happy to help you and send you materials.
Right. That's awesome. That's awesome. And it's just cool to see educators log in.
It is.
And get something out of this. That
thrills me.
Yep.
I also, every once in a while, Scott, get requests from educators around the world to appear in a video conference, teaching conference by Zoom or whatever.
Yeah.
And if I can, I'm always happy to accept those invitations to speak to professional associations, groups of teachers around the world, and help them improve education in your own home country. My only fluent language is English, so that may be a limitation, but apart from that, anyone who wants to reach out to me at astronomyforeducators@gmail.com is welcome to contact me. And I do probably about 50 or 60 educational outreach events a year.
That's a lot.
And I do more and more overseas by basically the same way we're doing it today. So I can appear and help your teachers in
Zoom and the
country.
internet has made a lot of that possible. So that's
it has. Cool. It's wonderful living in the future.
Yeah. A nice comment here. It says, thanks, Dr. Barth. Definitely clearing up misconceptions that I've had. Now I have to remember who told what and make the corrections.
Oh, golly. Okay. Well, right. I'm happy
to the teaching guide. So it's
good. I'm really thrilled to teaching is kind of like starting an avalanche, isn't it? It's standing at the top of a hill, knowledge that you've struggled and climbed and gained, and then you throw rocks down the hill, right? And you try to get people started on their own journey. And many times it's just a rock on a hill, but every once in a while you start a real cascade, and it's a beautiful thing to see. And no one's buried at the debris at the bottom, so it's all good.
That's right.
I'm thrilled if this program is helping start people on their own journey.
Yeah.
And that's really exciting. And next week, we're going to be taking a look at some more practical activities. And one of the things we're going to be taking a look at is, again, following in the footsteps of Galileo. And we're going to be taking a look at the moons of Jupiter and how to observe them, how to identify them, and what we can learn about orbits. And actually, you can deduce a fair amount of Kepler's laws of planetary motion by watching the moons.
Oh, very cool.
And that's very exciting. So we're going to wander a little bit deeper into the mathematical end next time. Mm-hmm. We're also making progress on the observatory here at Barthland Ranch.
Oh, that's cool.
And so we're starting to get bits and pieces that are going to be for the observatory, which are coming in. And I'll be the ones that are hand sized, I'll be showing off. And as we get some footings and foundation and concrete and piers and things poured, I'll be sharing those with our friends here on How Do You Know in weeks to come. Great. And very exciting summer here at the ranch.
Right.
Also, I'm working on more writing for more people. And a lot of it is kind of on spec by request. Could you tell us about this? Could you tell us about that? Friends out in the audience, if you have a request for a particular show, I don't have a pet black hole, so we can't.
A pet black hole.
We cannot bring a neutron star into the science lair, into our studio here.
All right.
But if you have an idea for a show or something you'd like to see, we'd be happy to take your suggestions. And I see we have Cameron Gillis coming on, which is really exciting.
Yeah.
He's
So,
going to be following
yeah, Cameron's
on. There's
part of our
Cameron.
double feature today, and it's his first program, CAMSTRONOMY, and his journey of astronomy and reporting, recording his observations and all of that. So it's really cool. And so we're going to take a 10-minute break here, and then we're going to come back to Cameron, or maybe a 5-minute break, and we'll come back to Cameron, and we'll see you guys in a little bit. Anything else you want to add?
I'm looking forward to Cameron's program.
Okay.
I'm setting up my big refractor in a couple of weeks here in a permanent spot. So I'm looking forward to seeing what he has to say. And I hope everybody will stay tuned, because it's going to be another exciting program brought to you by our friends at Explore Scientific.
Hey.
Yay.
All right. Yeah. Thanks.
All right.
Thanks, Dan.
All
Thanks,
right.
Scott.
Bye-bye, everybody.
Okay.
Thanks.
All right.
Yep.
Take
All
care,
right.
Dan.
Good stuff. Yeah, thank you.
Okay, so we're going to take this break right now, and we will be back here in just about 5 minutes.
All right.
And I will be right back.
You bet.
Well, everybody, we are back, and it's great to be here with you with Cameron Gillis. Cameron kind of dived into telling me a little bit more about his background and stuff. The guy starts in astronomy when he's only 14 years old. And through that, he had a brand new 4-inch Newtonian. He saw Saturn. That's what propelled him into his journey of astronomy. And he eventually gets aperture fever and gets an 18-inch obsession Dobsonian telescope. And so it's cool seeing pictures of him with his scope. He's been on our program, so the Global Star Party, several times, and he has really made a very nice contribution showing people how they can make excellent celestial images with a smartphone, but how they can go in and make observational records of what they're doing. And that was really the first steps to doing science. And so, there's so much more to tell, but I think that you're a technology engineer for, is it Samsung? Is that right, Cameron?
Yes, Samsung Networks. Yes, working on 5G. Yeah.
Okay, working on the 5G network. So that's really cool. So what you'll see later as we do more of these programs, we're putting together a web page for Cameron for his series. There'll be a bio about him that you'll be able to read a lot more about Cameron and his adventure. But the whole emphasis of this program is to help you on your journey as Cameron goes on his. And so that's why he's calling it CAMSTRONOMY. So, or CAMSTRONOMY, excuse me. So, Cameron, I'm going to turn it over to you and let you take it over.
Thanks a lot, Scott. Okay, so let me just share my screen. So hello, everyone, and great to be here. And thanks, Scott, for setting this up. This is, I really appreciate it. And it's wonderful what I've discovered since this COVID situation has hit us all. It's really wonderful to be able to contribute and kind of dive into astronomy and enjoy the night skies and share that with the broader community. So it's really great to be able to be part of that and to help out. I mean, on one hand, I have a lot of experience observing. On the other hand, there's a lot to learn. I mean, the universe is vast, and there's a lot of different skills. And what I want to do is share my my journey of how I methodically kind of re-entered astronomy from the old pencil and paper way with recording things on my Sky Atlas 2000, and move on to all the new digital age with smartphones, with tablets and all the different tools that we have at our disposal, and eventually go to imaging. So what I've done, and let me just kind of actually share my screen here. Let's see, share. I'll put it into presentation mode here. Okay. And I'll make sure that it's you can see the whole screen here. I think it's give me a second, it's showing the presentation. There we are, duplicate slideshow. So just a little bit about myself. I have a timeline.
There we go. All right, now
yeah.
we're in.
Okay. Yeah. Thanks. I built this timeline of the telescopes I've had since I was 14, as Scott highlighted. I started off with a 4-inch, just a simple alt-azimuth Newtonian. It was great. That's where I first saw the rings of Saturn, and it was a crisp morning. at 4 o'clock, and it was wonderful. It was rising, and it was in good view, and I never forget that. And of course, ever since then, I started getting more advanced. I wanted an equatorial, so I got a 6-inch. I figured that 6-inch you could see a lot more, and I had, this was in Canada, and then I started getting into I wanted higher quality optics, and something that I could use and take with me, and I ended up getting a 4-inch Renaissance, which was a beautiful scope, really good, very similar. It was a fluorite doublet, and quite nice images with that. And then, but I also had a pair of 11 by 80 binoculars as well, so that was great that was where I saw the Milky Way for the first time in remote Canada, rising one spring or summer evening, and it was just amazing to see Andromeda Galaxy, of course, and scan the Milky Way with that. So, and then as you said, Scott, I got my aperture fever.
Yes.
I basically when I was in Canada, I went to some star parties, and I actually had the fortune of, in the Royal Astronomical Society, I had the fortune of viewing a 17.5-inch. Back then, they had a 17.5-inch, and I never forget. I think it was the antenna galaxies, or some of the Virgo galaxies that were just incredible. You could see structure, and you could see, the wisps of nebulosity, or the spiral arms going off, and it was just fantastic. So that image was burned in my mind. So I always promised myself, when I can afford it, and the time was right, I would get myself a large telescope, which I did in 2005. I ended up, and this is me setting it up in my living room. And I was so inspired, and it was so wonderful to be able to enjoy. And I just started diving into all the galaxies and galaxy clusters, down to 15th magnitude. And it was just wonderful. And I started logging a lot of I had my Sky Atlas 2000, and I actually had Uranometry at 2000 as well, because that's an excellent guide. And back then, that was the de facto, Bible, if you will, of if you wanted to observe, it had stars down to 9th magnitude, so you could really do star hopping and really triangulate and identify all the different unique galaxies and galaxy clusters with that. So I really had a blast with that. And I remember my benchmark when I was observing through the 18-inch. My benchmark for when I was dark adapted was to always look at M51, and I could detect the spiral arms and structure within them. That's how wonderful it was. It was just really nice to be able to see M51, like the spiral arm structure, visually, with this scope. And so I had a really nice experience with that, kept it for many years. And then I also, it was on the cusp of when go-to telescopes were going, and I started wanting to have a little more grab and go telescope again, that took advantage of go-to technology. So I ended up getting a 6-inch Next Star. I spelled that wrong, but anyhow, then basically that was really good. But I also learned, this is kind of, being an observer. I have to say, the obsession, it was really nice. It was very simple. It was just elegant, no bones, no bells and whistles, very straightforward, just pure aperture, very smooth motion, mechanically excellent. So that was a very transparent experience. When I moved to the go-to, I was always, I was thinking, okay, it's good, but you, like you said before, and I'll say it again as experience. Yeah, you kind of have to know your way around the sky, and you start to think about the details about your flow, right? Of how you do your observing, and that. And I found that it was good, but I missed having the ability to be able to just switch and disengage the go-to, and then just star hop to another galaxy and then track. So that was kind of my beef with that. I enjoyed it. It was good scope, but I realized it wasn't quite there yet. So then I got really busy. This was kind of the peak of my my career around 2010 and onwards. That was a very, very busy time, and I didn't have as much time to observe. So you'll notice that I have around 2019, I actually sold both of those telescopes. It was a very hard decision, but my logic was, the old saying, the best scope is the one you use all
It's
the
the one you
time.
use. That's
and
true.
and and it really, I cannot say it enough. And I've seen enough of the good stuff that I knew that I would get there again. And also imaging was starting to come up, and with these smaller aperture telescopes, you can start to see things that you can see with a larger aperture and a much more convenient package. So I figured, you know what, I there were some good people that were interested in it, and so I sold my scopes, and it was very nice to find a new home and be utilized. So then I switched over, starting off. I ordered an Explorer Scientific ED80. I had a Skywatcher Mac 102, and then I also got my 8-inch Schmidt-Cassegrain. So I kind of retooled, and I figured my decision for all these was the Skywatcher, the Mac is I have to say, probably the best bang for the buck. I mean, really cheap, great quality optics. The only thing is you have high focal length, so low, very good contrast, but very limited field of view. So that's kind of the challenge, but a great grab and go, fantastic for planets. Really enjoy it. Obviously on the ED80 side, fantastic, just beautiful wide field views, gorgeous. And you'll notice that I had a little time. I had the carbon fiber version, but then what I wanted to do is upgrade, because I want to go to imaging. And so I decided to go for the ED80 FCD 100, which is still, I'm still waiting for, Scott, but yes. I can't wait, because my experience with the ED80 FCD one was really good. And now I'm willing to, I really want like premium optics. I'm very fussy guy
Yeah.
when it comes to observing. So I want to have like perfect double star resolution, and also beautiful wide field. So I'm waiting for that. But those are great complementary between the ED80 and the Mac 102. Wonderful complementary scopes for handling planetary and grab and go. And what I wanted, and then I have my Evolution 8. Now this is about the mount. I must say, why I went for this is because I like the disengaged clutch. It had the go-to technology. It has built-in Wi-Fi, built-in battery. So really, you just grab this thing, you set it up, and then I also have a tablet that's paired with this, so that I can have Sky Safari tethered to it. And another program I'll show you, what actually physically what my setup is, and then basically it's all connected. So I can, when we go to the Sky Safari portion of this session here, I'll show you how I control it and come up with my list, and I'm able to log and very much categorize all my observations more than I was ever able to do with my 18-inch, simply because of the convenience of having everything at the fingertips. I wouldn't have to go to my Sky Atlas 2000, use my flashlight, look at where I'm going, and go back and forth between the eyepiece and the chair. I would be able, with this new setup, you can just sit there and everything is right there. You can literally look over at the tablet, get your visual plate solve, and then go back. So a wonderful package, very, very good scope, and the aperture is just the right size. I was thinking about a 9 1/4, but it came down to size. This size, I can actually put this on shelf. I can put it in its foam casing and put it back into shelves, and I can store it very nicely. So it's very, very convenient for storage as well. Anyhow, so now this is where I'm at. So now if I look at the equipment, I have my Skywatcher set up. I'm using the maximum field on the 102, the Mac 102, is this 26 millimeter 62 degree Explorer Scientific eyepiece, which I got a couple of months ago. It's a fantastic eyepiece. It gives me the maximum field of view. And I'm actually enjoying, I have a set of Naglers that I've had for many years, and they're great. The 82 degree, it's beautiful. But I have to say, I really am enjoying the eye relief and and being able to see the sharp edge of field of view with this type of eyepiece. So the other advantage of this with inch and a quarter eyepieces is I can couple my my NextYZ phone adapter and do smartphone snapshots, which I'll show you a little later. And basically very conveniently get the full field of view. And then of course I have my smartphone that I couple it. This is when I started this, coupling my smartphone to the eyepiece, I started taking pictures. I really was impressed with how far, you know, the smartphone camera technology has gone for astrophotography. I mean, you can really it gets you to the point where you realize that you can take some very simple pictures. You can enhance what you can see through the eyepiece, and it really is again a very complementary tool to be able to improve your observations and your record keeping, and also at the same time be able to share and enjoy. So what I'll be doing, but I've also noticed on the flip side is, and this is, you know, getting to the next stage, is it kind of makes you want to have more in terms of more automation and a better flow for recording. And that's why I'm going to I'm getting an astro imager, a dedicated astro camera that I can plug in. And the big advantage, of course, of that is you can set up in Sequence Generator Pro, you can set up, you know, a number of sessions all together, but have a better operations. Smartphone is great and it's good for live and quick shots. Again, grab and go, very nice. But I want to complement that with this program with a astro imager. So I'll be sharing that in the future. And then this is what I have on my Explorer, sorry, my 8-inch Mikasa grain. I got the 40 millimeter, again, similar to the Mac 102. The Mac 102 with the 26 millimeter is the biggest field of view for the 1.25 inch. The largest field of view for a 2-inch is, which I have a 2-inch diagonal on my 8-inch, it is 40 millimeter and beautiful. I love this. This is actually, I bought this first at the beginning of the year from you, Scott, and that actually encouraged me to get the 26 millimeter. And again, this 68 degrees, again, not as wide as a Nagler, and you know, or as your 68 or even 100 degree, which eventually I would like to get. But I do really like actually a little bit narrower field of view. It's also better for even for smartphone. I can actually couple my smartphone on the 40 millimeter around the eye cup here. I have done that, and if I'm careful with it, it won't fall off. so basically, but that gives you really nice, you know, it gives a full field of view, and it gives you excellent eye relief, and it's a beautiful one. But I must say, after having said all that, my go-to eyepiece for all my galaxy observing and what we'll be talking about in the program is still the 13 millimeter Nagler 82. That gives me a really good power, about 156 power, which gives me a good enough contrast, because as an experienced observer knows, there's kind of a threshold where you need to darken the sky, the background sky, especially with light pollution, enough to improve that contrast, but you don't want to darken it so much that you wash out the surface brightness. So that seems to be the sweet spot for me when observing, because it gives me about a 0.5 degree field of view, which is pretty good. And then so I can actually see the whole moon in it as well, and it gives you enough resolution, but at the same time a good field of view. So that's a beautiful eyepiece, and it also couples nicely with the smartphone. And then, like I said, for controlling all this, I have my tablet. So this is a snapshot, and now we're kind of switching over to the Sky Survey part. I'm using Sky Safari for logging all my observations, and I've moved over from an Excel-based tool, which I'll share my screen here. Let me just go. Where's my here it is. So if I look at my observing list, before I got Sky Safari, it's coming up here. Yeah. So here was my observing list before I had Sky Safari. So what I did is I went and I did a search online, and I got the database from the NGC IC project, which was a website that was active about 10 years ago. I think they don't update it anymore. But anyhow, I uploaded all that, and I started categorizing, based on the magnitude and the size, whether I can observe it. And then I have different tabs here. These are my observations from my obsession. And then these are my observations for my Evolution 8, my Skywatcher Mach 102, and of course my where is it, 6SE, and my ED80. So I have this for every single one, and this is quite a bit of, it's quite a huge project, but basically my objective in constructing this is to obviously first of all have a record of everything I've seen, so in digital format.
Very
and then the second thing is to basically for every different scope. But what I've learned is, sure, with 18-inch you can see galaxy clusters down to 15th magnitude and even 16th, and it's great, but there's literally thousands and thousands of objects that you can still see with smaller apertures. So I was realizing that with a go-to and this going through and kind of combing through and doing a sky survey, you can have just as much fun, if not more, by going and just getting everything below 12th magnitude, let's say, right? And start to categorize that into different apertures and saying, okay, what can I see with an 80 millimeter? What can I see? And you'd be surprised, and you pointed this out another time, Scott, you'd be surprised what you can see with the small aperture telescope when you actually start digging and going through. The real frustrating part when you're starting out, and I had this when I first got SkyAtlas 2000, is when you look at SkyAtlas 2000, you just see a bunch of red galaxies there, and you don't know their magnitude, you don't know their surface brightness, and you might look there and it might be a hopeless search, right? You might never find it, and you spend hours or many, long time trying to find objects that are just not detectable. So what I with the go-to and with visual plate solve, with Sky Safari, going back here, I'm able to actually categorize everything and right away go through every object, see what I can see, and then categorize whether it's even possible to see in a smaller aperture. So I'm using my 8-inch right now, and then of course I'm going to follow through with photographs, with astrophotographs with my astro imager to basically categorize, and then we can have at the end of all this, as we go through this journey, we're going to have. It's going to take a long time, of course, but you're going to have a database where you're going to be able to say, okay, what objects can I see tonight? And then you'll be able to, like, here's my mapping. I have the coordinates mapped. This is my Excel version of the map of all the objects you can see. This is the way I did it back then, but now I can do everything with Sky Safari. And let me now switch to Sky Safari and show you what I can do. So I'm going to connect. Oh, let me just turn off. I have Stellarium in the background too, so let me just connect here. Share my screen. There we go. What I'm doing now is I found out there's a way you can, just like you use Chromecast or whatever, you can
Okay.
do that here. You can actually do that with from your tablet to your PC, and that's what I'm doing right now. So,
Very cool.
so now as I'm playing with the tablet, you can see what I'm doing. So I'm going to turn off. This is every object that I've categorized as best in what I call best in brightness um, over the last year. And if I go to observing lists, see best and brightest, you can see is 681 objects, right? 681 objects I've categorized in best and brightest, and they're all listed here. And if I turn it now back to horizon mode, this will be more easy to understand. And I go south. Okay, so this is what the sky will look like at midnight. Let me just look at the time here. Yeah, so at tomorrow, well, at midnight tonight, let's see, it will basically look like this, and you can see that based on the density, you can see where a lot of the objects, like this is the Virgo cluster of galaxies, so there's quite a bit of objects there, and then as you go towards the east, you can see the Milky Way, and you can see all the open clusters and the nebulae. Those are all along the galactic plane, and then but you'll notice also there's some dead spots where, and for example, this one here, Libra, I haven't actually. This is one of the constellations I haven't completed yet in my survey. But what I've done, for example, I started off last year in Booties. So if I go to Booties and I go to my observing lists, here are all the different observing lists that I've created. So you saw the Excel version that I showed before where I did everything manually. Well, what I do here is I can create a new observing list, and I've created ones for each constellation that is in the northern hemisphere. So for example, I started off initially categorizing by different magnitudes. You can see there's a magnitude 8 list, 411 objects, southern hemisphere. So when I do eventually get to the south, I have my top objects of magnitude 8 and brighter, 156 objects there, etc., right down to magnitude 12, 587. So if you tally all this up, you'll notice that if I go down to the bottom, actually, no, this is fine. If you add it all up, it's around about 1,000 to 1,500 objects that you can see down to 12th magnitude. And then if I go constellation by constellation, I created, for example, Booties, Libra, Corona Borealis. You can see the number of objects on the right here. Those are all, what I did is I go and create an observing list, and I go planner. You click on planner, and I did open clusters, globular clusters, bright nebula, planetary nebula, and galaxies. You can put a lot of other objects, but those are the main deep sky objects that I would select. And then I would go down to magnitude 12. So I type in 12. And then you can specify size. You can do a lot of different filters, but I just wanted to do magnitude 12. And then I would choose the constellation. So let's say we're starting off with Booties. And I go do search. And you see there's 12 objects. So then if I create the list, make it into observing list, it says observing list created. And then if I go to my observing list, oops, sorry. go back here, observing list, and you go to the bottom, search results, 12. And then what you can do is you can go actions, highlight objects. These are the 12 objects down to 12, magnitude 12 that are in booties. And what you can do once you've created that, and I've done that for every constellation, let's say I'm observing this IC 983, and I put a little comment and say, okay, create new observation. Actually, what I can do is I can go observing lists. This is important. So let's first of all, let's just call it booties 2. Booties 2. Okay, oops. And we're gonna go, and yeah, and I go, that's fine. And here's the important thing. You see there's all observed and unobserved. What I do is I go unobserved. So when I'm starting my session for tonight or whichever night, I go unobserved. And then once you've highlighted that, it will only highlight the ones you haven't observed. So then in that list that you created, so you can keep on creating new lists every time and basically start a new observing list and then start refresh. But once you create an observation here, so let's create new observation. And then I can type in, you know, I can say, let's say faint, oops, faint oval patch near triangle, triangle of stars, let's say.
Okay.
For example. And then you put in the seeing conditions, let's say it's slight quivering. And then I put in my equipment, and you can see here in my list of equipment, I have my Mac 102.
Drop down. That's cool.
Yeah, yeah. You get your drop down. You got your Mac 102. My Evolution. I have a 6.3 focal reducer for that, and then I also have my 80 millimeter Explorer Scientific. All of that's there. But I'm going to say I'm observing that with my next star.
Yeah, and this is all Sky Safari Pro 6, right?
This is Sky Safari Pro 6, correct? That's right. And then I go like this, and guess what? See, it disappears. So you can actually, as you go through, and then you say, okay, I want to go to the next object, etc. So I can go here, and then once I can flip that around, and I can go observing lists, booties 2, and I can say observed. Now it will only show that observed object. So you can go through and see what objects. The other thing it does is if you go sessions, you'll see these are all my sessions. This is my, you can see one observation I made today at 12:30 a.m. and that's the time that I had in Sky Safari. That was the one observation. As you can see here, actually, since we're already here, you can see all of, I haven't titled them all, but these are my observations over the past year. So if I the last time I had a clear night here in Seattle was Sunday, May 9th, and I started my observing session at local time 9:54. And I have 48 observations. And if I click on that, it doesn't tell me anything except for the time, but I can actually look at which observations I made. And if I go way back here to the beginning of when I started, see, I started almost a year ago, my Evolution 8 in booties, 11 observations. That was my first night, 622, my first light with the 8-inch. And then I continued 30 observations, 9, etc., etc. And then then I had a really wild night on July 18th last year, 141 objects. I was going crazy in the Milky Way. It was an all-nighter. And I observed, I have made 141 observations. And I did that all the way through in my Sky Survey. And I have a record of every day and the number of observations. So you can see some nights was very little. Other nights I made, I think on the average, if I have a good night, without getting stressed out, I can do 40, let's say 40 good observations a night. Some of the
Good.
ones that were, yeah, which is pretty good. And then of course I want to enhance this to so now if you tally that all up and we look at my observing lists, you know, all these objects starting off again, going back to Booties where I started at the beginning here. I sorted these, you can sort these constellations as they go around the meridian, as they pass the meridian and through the seasons. So Booties, Libra, etc., all the way through. And most of these objects now I've actually observed. I don't have a compiled list of how many observations I've made. I can probably add it up, and I'll do that at some point. But I've literally seen thousands of objects over the last year. When you add up all these numbers here, especially Virgo, 296 objects in Virgo. That took me about 4 nights to do it properly. I kind of took bites out of it. You know, the Virgo is this high density. So basically, I started to eat into that, and then after I've done those observations, so let's say I finished Booties, you can see there's 55 objects that I observed, but then I go back and I go best and brightest, and I go all. Best and brightest, I have 681 objects, okay, that I've categorized out of the, let's say, 1,500 objects that I've seen, or over the last year. 681, and you can see, so actually the galaxy that I chose earlier, NGC 5490, it was one of those that actually categorized as what I consider the best and brightest. And how do I do that? What I do is I have a descriptor which is called distinct oval patch versus faint oval patch or diffuse oval patch. If it's distinct, then that means I can clearly, there's enough surface brightness that I can clearly distinguish it from the background, and it doesn't look like a out of focus star, and I can clearly see it's a galaxy. Beyond that, I might have been able to detect it with averted vision, but I don't. You'll see there's many galaxies here, and like these ones up here, it's at magnitude 12.7, NGC 5548. And if I look at my description, show observation, faint oval with slight brighter nucleus. So I was able to see some difference in surface brightness, but I didn't categorize it as a best and brightest object. So what I do is I comb through and I start to add those objects to my, you can actually add those objects to the best and brightest category. And then those are the ones I'm going to go back and re-observe with smaller telescopes to kind of see if they're detectable, and then do a side-by-side comparison. And then I'm also going to be doing imaging as well. So I'm going to come back here, but let me stop sharing for a second. Let's stop sharing. I'm going to switch over to some pictures now with my smartphone. How do I do that? Oh yeah, stop, I'll disconnect. Okay, so now we go back to my presentation. And then, so let me put it back into presentation mode. And make sure that it's duplicate slideshow. Okay, so moving on from Sky Safari, I'm starting to take some smart. So here's the latest picture I wanted to share with you just yesterday, and I'll let you guess what it is.
Yeah, the sombrero.
Sombrero Galaxy M104. That's right. And what I did here is I stuck this on my 13mm Nagler with my smartphone on my 8-inch, and I took a 30-second 1600 ISO picture, and then I zoomed it ×2 on as you can see there's some vignetting up here, but the point of this is that when I look through the eyepiece, I can barely see, this other side of the dust lane. So visually, I definitely it's quite a bright galaxy. You can see it, but this part here is very elusive, because of the high surface brightness of my light pollution. But with the smartphone, I'm able to eke that out, which is really nice. So it's not a nice picture, I mean, compared to obviously what a lot of the professionals do. But the fact that you can get a better view with a smartphone than you can with your eye, I think says a lot. And it really enhances the experience for anyone. And I encourage anyone to use a smartphone kind of as an enhancement, right? The other advantage of smartphone is you don't need to dark adapt, right? You can look at the objects and you don't have to be dark adapted. So there's a lot of advantages. So this one I just threw in this. This is a Stargate, which is nearby. Stargate plus asterism, close to M104. Here, this one here is a lot more elusive. You can't guess this one. I'll tell you what it is. It's actually the antenna galaxies, and I haven't stretched it or anything. This is all when I just emailed myself from my phone, and then a 10% compression. So really, like, I see lots of noise. This is not. But the point is that I can see actually a little. If you look carefully, you can actually see a little bit of structure of the two antenna. Here's one galaxy down here, and then you see the loops over here, but it's not clear. But this is what I hope to achieve with my astro imaging setup, to get a little more clarity, because this is, frankly, this is already better than what you can see visually. Visually, you can you can see the two ovals barely, and you can see hints of the antenna wisps arcing out, but very, very, very subtle, and it's very elusive. But when you see with the smartphone, it's very clear. But obviously with astro imaging, and then with a little bit of processing and stacking, it will be that much more enjoyable. Again, my objective with my astro imaging is not to make the prettiest pictures, but to make clear pictures that help augment the observing, experiencing, and the cataloging of all the objects as part of the Sky Survey. Here is M3. It's a little fuzzy, globular cluster, and yeah, M3, and yeah. So trying to some variety. I really love globular clusters too, because it's really nice. I'm impressed, and obviously with 18-inch globular clusters are just amazing, right? I mean, most globular clusters are resolved to the core, but it's really nice to be able to, with an 8-inch, visually you can see still quite a bit in the brighter ones. You can actually see the resolve even to the core, but with the smartphone, it just captures it really nice. And you can see the different brightnesses, and obviously I can make a sharper picture here, but this was just the one I had. And on the right, we have the Eskimo Nebula, or Clown Face Nebula. You can see the outer parka, or the outer ring, and the inner ring is kind of semi-triangular. That's a beautiful. I love this object because it has a memory to me in several memorable moments. When one of the first objects I saw with my 18-inch obsession was actually the Eskimo Nebula. I was actually trying to look at Saturn. Saturn was in Gemini at that time, and I was doing some star hopping, and it just happened that Eskimo Nebula was within the same field, or like really close by, and was like, oh my gosh, I was like blown away. It's just a beautiful object. Anyhow, and then here's a picture of the ghost of Jupiter on the right. And again, what I want to do with all of this is I just threw these pictures in for today's session, but I want to have a more structured approach where I basically label and will go through my Sky Survey with a complement of the constellation, the objects, and kind of show what, kind of describe what I've seen visually, and also help share what you can see with different apertures. Here you have I love this M106. Again, with the smartphone, 30 seconds, 1600 ISO is the magic formula for pro mode, and that gives you pretty good clarity, not as much noise, and you can see that beautiful dust in the center nucleus, and you can see the arcing. And again, with just a little bit of stretching, you can probably pull out the spiral arms. But visually, again, it looks very good. What's interesting when I compare visually is visually it's brighter overall, but I don't see as much detail. Like, for example, I cannot see this dust lane as clear. You can see it's there, but you don't see it where you're able to focus on it with direct vision when you have, compared to averted vision when you use the smartphone. So really the smartphone allows you to see direct, it lets you enhance your averted vision visually with direct vision. So that, I think that's pretty much what I've discovered. Here is M51. Again, in my 18-inch, I would see a much even better view than this. But this, I was impressed with an 8-inch. You can actually visually start to see the hint of spiral arms. It is actually possible. But again, with the smartphone, you can pull out the direct vision. You can actually very clearly see the spiral arms. And again, with some stretching, you can eke out some more. And so this is kind of what I had. I used Stellarium. This is what I'm going to do. A combination of Stellarium, because it gives you a nice simplified view. I can do the same thing with Sky Safari, but again, use every tool at your disposal. So Sky Safari, great for recording, great for zooming in and analyzing, and visually plate solving. But I love Stellarium is great because it's very simple and it's good on the PC to be able to identify. So I will go through the constellations and highlight the different objects, and then we'll have a kind of a picture and a description for each one. And I think, let me switch back to, so as an example, let's take, which object do I want to choose? Yeah, I'll choose the Eskimo Nebula. Okay, so we'll keep that one there, and then let me share my screen again. Connect. There we go. Reshare my screen here. Okay, so what I'm going to do is let's go to the Eskimo Nebula. So I'm going to go search, and then type in Eskimo Nebula. And there it is. And it actually, this is obviously a better image, but it's kind of neat how you could recognize a lot of the same structure even with a smartphone. And I'm looking forward to doing the same with my Astro Imager. Let's see here, and I go center on object, so it automatically moves over. It's below the horizon, but let me go back a couple hours and bring it above the horizon. Okay, there it is. And let's zoom in. And this is my, let me turn off the time. So this is my field of view with my, if I actually go for my scope display, I have all my eyepieces for every telescope. So I have my 5, 7, 13, 26 for the Mako 102. Those are all 1.25 inch. I have the same for my ED80 already ready. but I also have added the 40 millimeter because it's a 2-inch. It has a 2-inch diagonal. And you just look at the field of view, right? 5.67 degrees on this baby. They're really gonna, this is beautiful. This is beautiful. Can't wait. And then if I look at my main one I'm using right now, I use my 13 millimeter, half a degree, 156 power, exit pupil 1.3. So that's my my field. Just for fun, I'm going to put the 40 millimeter 40 millimeter on the ED80 just to compare for fun. So if I zoom out, look at this, right? This is the field of view difference using the 40 millimeter on the ED80 compared to the 13 millimeter on the 8-inch. But anyhow, my point of showing this is you can see the star, that's the bright star right beside the Eskimo Nebula compared to the to this picture. So what you can do, and then if we look at other objects, you can actually do triangulation on where the objects are. So basically, between when I'm actually searching for fainter objects, the visual plate solving ability is really great. The other, that's what this is with Sky Safari. If you use Stellarium, which I won't do right now. Well, yeah, let's do Stellarium. Why not? Let me just oops, Stellarium. Okay. And the advantage of Stellarium, which I really like, and this is what I want to show you, and we'll use this as well, is it has the ability to put the eyepiece view, which flips the view, which is really important. So I'm going to change the time. Let's make it, okay, so let's look for the Eskimo Nebula. Let's turn on the constellations so I can, oops, yeah, there, and the Eskimo Nebula is right here. So again, as a visual observer, you start to, you know how to star hop to stuff, and then if you zoom in here, let me just turn on the, so we can find it. DSO. There it is. Okay. So same thing here, but here's the difference. Right now, you see the same stars, but if I click on it and I put on the eyepiece view, it flips it. So you'll see, if I turn off this, you see that? If I go to this mode, it flips it. So what's really nice about Stellarium is you can actually do it. Even though the stars and the plate solving isn't as, you know, nice, as crisp as the Sky Safari, it does have this ability to flip and see what it looks like for you. In this case, I had it on my the 26 millimeter on my Mac 102. But anyhow, that's, and then what you can do is it will help you with the it will help you with the visual plate solve. So I think that's that is it for now. And what I'll do is going, oops, let me just reshare my screen here. So going forward, what I'm going to do is we'll start to go through the constellations and the objects, and I'll share with you the observations, and then I'll also give you updates on my my equipment that I'm using. So going from smartphones, of course, and any new images I take with my smartphone, and of course, as I add the imaging, it's probably going to be arriving in about a month, and I still need to learn about that. I have an ASI Air Pro that's going to be coupled with an ASI a ZWO 294 4/3 sensor, And if I show you what I'm going to be doing is with my smartphone, I'll be able to take pictures with the field of view that you see here. But if I turn on the ASI 294, I'm going to use the f6.3. I'm going to put on the focal reducer. So this is gives me a 0.86 by 0.58 field of view. So if I go back here, this is going to be the view of the image sensor. So the smartphone is the circle, you can say, on my 13 millimeter Nagler, and then the ASI 294 is going to be like this. So then we're going to be able to look at objects, and that way we can take this journey together, and I'll share, the objects, and then everyone can look themselves at the different objects. And I really want to discover the nuggets, because we all know it's always fun to look at and image and describe and observe the brightest objects.
Mm-hmm.
But it's also fun to find some of the fainter objects and challenge at each aperture, right? Because after you've seen so many galaxies like I have, and many of you have already seen, you see that at a certain point, there's the fainter ones all kind of look the same. So if you look at an 18-inch 15th magnitude, it's the same as looking, let's say, at a 12 magnitude in a 3-inch, right, in an 80 millimeter. So it gives you the same type of excitement to be able to discover that same equivalent challenge object, regardless. And there's thousands of objects out there. So the real fun part, and what to make this fun, and what I want to achieve out of this sharing, is I want to reduce the frustration for people, so that that you are truly looking at a challenge, not an object, rather than an impossible object, right? You don't want to be looking for something you can't find, or you don't have any hope of finding. So anyhow, yeah, I think that's any questions or comments, Scott?
People are saying thank you for your presentation. They're saying it's a lot to digest, but they can watch it in in rerun here. And a lot of people are wanting to know if they can get Sky Safari on their PC.
Yes, and I'm actually in the process of doing that. What you can do is you can download this Blue Shield or Blue River or something like that. I have to take a look, and it's basically a smartphone emulator, and that's what I'm planning to use. And I'll find out what that is. Again, this is part of the journey. I'm setting it up so that, just like the person asked, you can basically take this, if you already have it on your smartphone and you want to put it on your PC, you just download this emulator, and then you can run the whole thing as if with full functionality.
Okay. Well, great.
Yeah.
Great. So we'll watch that next time. So we'll see you next Wednesday. And probably we'll be on the First Light Chronicles hour as well. So same time, same channel, same everything. And we're looking forward to more.
Awesome.
So Cameron, thank you very much. It was a lot to go through, but I think you did it in an excellent way. So thanks very much.
Thanks a lot. Yeah, and we'll do it more digestible in the future. I just wanted to kind of get a sampling. Yeah, an overview.
Right.
Yeah. Thanks a lot. I really
right.
appreciate it. Good. Thanks everyone. Thanks, Scott.
Thank you so much, Cameron. Up next at 7 o'clock Central, in another hour, will be Caitlin Ahrens, and Caitlin will offer her first install of 7 months of science, which will run each month. And you can see it on the explorescientific.com/live on our calendar, and see all those shows. But this is the first one tonight, and Paul Knightley will talk about his experience in being with a research team to simulate what it would be like to be a colonist on Mars. And so these guys actually did this, and he'll describe the whole process. It's kind of like I guess similar to a biosphere experience, but I think in much smaller quarters and with lots of communication delays and stuff like that. So looking forward to it. We'll see you then. Until that time, enjoy dinner, take a break, and we'll see you in about an hour. And Cameron, thank you so much.
Thank you, Scott. Thanks, everyone.
Take care.
Cheers. Bye-bye.
Good night.
Hello everybody, this is Scott Roberts from Explore Scientific, and today I want to talk about the world-famous Galileo telescope kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. The 25 hour, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barth lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope, so you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009, and it's a fantastic kit, both for child and adult, to learn how a telescope works. And so, if you get the telescope like this, you can either have it on a stand like this, you can handle it like a pirate's glass, or on the bottom here we have a threaded hole here that you can put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.